Good evening, everyone. Welcome to 60 Minutes in Space for July. I'm Dimitri Klebe, and I'm going to be joined with Kachun Yu, who's in the back here, for our monthly program. We always like to ask who's new in the audience today, and we're actually in a new audience. How many people are attending 60 Minutes for the first time? Well, it looks like about half of us out there. The other new thing that's going on is we're actually streaming this particular show to the website, and it's going to be available on on Facebook Live. So it's a new thing that we're doing here tonight. So for those of you who haven't been here before, 60 Minutes in Space is a program where several of us in the Space Science Department, me, Kachun, and Steve Lee, talk about what we think are kind of the new and exciting space science topics for the last month, or in this case, sometimes a few months. So without further ado, I'm going to actually get started on my part of the presentation, and mine is going to actually be on where I've actually been here in the last month. In the end of June, I went to Edinburgh, Scotland, where I attended this meeting on astronomical telescopes and instrumentation. It's a meeting that's held every couple years from the SPIE, and it is all the new technologies that are going on in the telescope world, in the astronomy world. So I'm going to talk about two of the presentations that I saw there that relate to some of the science stories, one of the science stories that I'm going to talk about. The first one I wanted to talk about was Hitoshi Murayama's talk on studying the birth and fate of the universe using multi-object spectroscopy. And so this is a big topic, and these are big telescopes looking at really big things going on in the universe. And he's also PI on this particular instrument, this SUMIRI, or the Subaru Measurements of Images in Redshifts. And this particular instrument, which I'll talk a little bit about, addresses some big topics, in particular about the expansion of the universe, or cosmic expansion. And we've been out measuring how the universe is expanding. Most of you probably know that we live in this expanding universe, but some of the very interesting things is that when we went out to measure that expansion, one of the things we found out is that expansion rate is actually increasing, and that's due to something we call dark energy. And if you look at the evolution of our universe, you see something like this that we portray, where you start off with the universe over here, you end up in this time over here, and you'll see that the expansion of the universe is comprised of like three separate phases. One is this really marked acceleration called inflation. Then it gets to this period where things are starting to slow down, but are slowing down due to the matter in the universe and something called dark matter. And then we're at a point in time now where that's turned over and things are starting to accelerate again due to something called dark energy. So if you look at that, the first part of inflation, we believe inflation occurred because the universe started in when it was very, very small, very, very early, a fraction of a second after the Big Bang, as what were called quantum fluctuations. And those quantum fluctuations ended up being magnified in this really rapid acceleration into what became what we see as the microwave background radiation there, which are those fluctuations imprinted on that. And we see this particular image of the universe out there when the universe is only about 370,000 years old. After that time, the universe was somewhat normal in the sense that it was slowing down, but in that process it went from a point where the universe was very, very smooth, where if you were to look how smooth that, it was like 1 millimeter ripples on a 100-meter deep ocean, that then went ultimately to the structure that we see in galaxies today. And it did it on the backbone of this material we call dark matter that came together to form the structure and the galaxies that we see. In our normal matter is in these structures, and obviously normal matter that make up the galaxies. So I should mention that these presentations I got from the speakers that were at the Edinburgh conference, and he liked to refer to the dark matter as kind of our mom. We were built, but we were together at the beginning, but now we've separated, and so we want to find what our mom is all about, and we want to find out what dark matter is all about. And then ultimately, we get to the later stages of evolution of our universe, where we have a universe that's speeding up, and it has this stuff that we call dark energy associated with it. And if you look back at this slide here again, all these three phases all are associated with things that we really don't understand. We don't know how this inflation happened and went from the quantum fluctuations to our existing galaxy, the microwave background radiation. We don't know what dark matter is. We presume it's there. That's one hope that we'll eventually figure that out in the next decade. And we don't know what dark energy is. Other than that, we know a lot about our universe. So it is linked to something very dark. There's a dark side of our universe here. So this is a slide they had on there, and the next slides that I wanted to show you was there also seems to be some weird things going on in Europe. And you remember when I went to this, Scotland, it was right after the referendum for Great Britain to actually leave the EU. So there's a little bit of expansion going on as well as they've moved out over here. And 2 years ago when I was actually in Scotland, I don't know if you know this, the Scottish people were trying to actually get out of the UK, and they decided ultimately to stay in the UK. And one of the arguments was that, you know, if you leave us, you're going to leave the EU. So they're considering about a move back in this direction over here. So now getting back to the universe thing. So one of the things that I'm going to talk about what this instrument does is if you look at the expansion of the universe as we currently understand it, the universe is currently made up of like 5% atoms, which are normal matter. And as the universe, say, expands by a factor of 2 in size, its volume goes up a factor of 8, and there's no more matter, so it gets diluted by a factor of 8. Dark matter, same thing, we don't know what it is, but it too, in that thing, would also get diluted by a factor of 8. Dark energy is one of these things where we don't know what it is, but it seems to behave as if you increase the volume by a factor of 8, the amount of dark energy goes up by a factor of 8. So dark energy is continuing to basically overwhelm the universe. But is it a factor of 8, or is it less, or is it more? And that ultimately determines what's going to go on in the fate of our universe. These things that are less potentially have the ability that the universe expansion can stop. Things that get greater than that, the universe will end up in something that's called a big rip. And the big rip has some significance in that if you look out at the galaxies that we see today, and ultimately those galaxies, if in this expanding and accelerating universe, will drop off our horizon so that we will no longer see them. And in fact, we won't be able to see the microwave background radiation. All those things that have led us to understanding this particular universe will no longer be there to observe. So in what is a long time, we'll only see these other stars. And so the author of this talk, he said he's still trying to raise a little bit of money for his instrument. He said, this is very important stuff, so we need to get some funding ASP because we're running out of time here to measure that. Okay, well, let's get to his instruments here. So the instruments are going to be on the Subaru Telescope, which is an 8-meter telescope on Mauna Kea and the Big Island, Hawaii. And there's 2 instruments that he's going to be utilizing, basically a camera and a spectrometer there. And I'll get into a little bit of the details of them. The thing about the camera is it's going to look at a very huge field of view, especially for a telescope of that size. Generally, the bigger telescopes have to look at a smaller and smaller field of view. So 1.5 degrees, which is about 3 full moons on a side. It's going to have a sensor well, let me show a picture of the camera itself. Imagine, I brought my SLR when I was out there to Scotland there, so I couldn't hold this one up there. But this is the camera that goes on back there, and here is ultimately the sensor there. It has 900 million pixels, so almost a gigapixel there. So it's tiled in this array. I think there was 116 of these that are 2,000 by 4,000 pixels, and that's what's going to ultimately be taking the images with this instrument. I believe they had the instrument, or maybe the two instruments were about $75 million for these, and they still need a few more million, but that's mainly funded. The imaging capability is going to be quite good. Here is a Hubble image over here. Here is an image for this camera, and I can't remember if it was simulated or if it's in operation at the moment. But you can see the resolution is quite good. It's never going to be as good as Hubble because it doesn't have to contend with the atmosphere. But to tile this many images together took the Hubble Space Telescope 640 orbits, 500 hours of integration. This instrument can do that in 2.5 hours and 3 colors. Okay, so it's doing a lot more. The spectrometer itself is, and I'm going to show you a movie later that shows this spectrometer there. It is a fiber spectrometer that feeds 4 different spectrometers, and each of those have 3 different channels associated with them. And so there's 600 fibers to each one, and there's the 3 different bands that allow that to get a spectrum of the galaxies that they want to take. Don't worry about the details of this, but how they're going to be measuring these parameters of the universe is through a technique called baryonic acoustic oscillations, where they look at different points in space, which is referred to by these different redshifts. A higher redshift is further away in space, so you're looking at an earlier point in time. And the technique basically is we look all the way back to the cosmic microwave background radiation. We see these little things imprinted on it. Those little fluctuations ultimately evolve to become galaxies. And the spacing on those fluctuations continues to translate through the evolution of our universe. So they get imprinted at galaxies at this redshift, which is 5.5 billion years ago. There's this one at 3.8, and they change. So, but they were eventually given by the cosmic microwave background radiation. Those spacings of galaxies basically represent what we call a standard ruler. Those spacings, we know what their origins were, and so as we track them through time, by looking at that distance, we can track the expansion of our universe. Well, to do that, you need to have lots of galaxies. So we're going from our microwave to our present-day galaxies, and we're looking at different epochs along here with an instrument like this, and seeing how those galaxies are ultimately spaced. And so that can actually then place constraints as you go at the higher redshifts on how the universe has been expanding, and therefore differentiate between, does dark energy go by a factor 8? Does it go factor of 9? Does it go factor of 7? So we're trying to get to those kind of details on the universe. And they need to get spectroscopy to do that. And so I think the next image I'm going to do is just their nice flashy little video of this particular instrument. It had sound to it, but it was a little bit strange and everything. But it's going to be answering lots of questions, like how the universe began. This refers to, how does it end? That refers to how dark energy plays in the role there. Why do we exist? Now that's a good one that's going to satisfy as well. And anyway, they're going to show, so you're looking at a distant galaxy. It's coming all the way to our Milky Way. It's going to come into our solar system. Our planets are miraculously aligned there as they come into the Subaru Telescope. And the way these spectrometers actually work is they'll go into the telescope, they come down to the focal plane, and the fibers that you're going to see here actually direct the light that's from the image plane into the spectrometers so that you can see what the spectrum of the particular galaxy. So they're all placed at where galaxies are going to be. This is going to be measuring millions and millions of galaxies out there, as well as doing imaging of them. And because what we want to do the spectroscopy for is we need to figure out how far those galaxies are away. You can kind of do it a little bit with imaging where you get different colors and you can get good candidates and things like that, but ultimately you need the spectra to give you what are the spectral lines so you can really see what its redshift is and therefore place it somewhere in the universe. And you've got to do it at a lot of galaxies because the only way you can use these baryonic acoustic oscillations to give you that kind of information to really get an accurate measure of the expansion of the universe is to have lots and lots of galaxies.